So anyway, there you go. So on to our next panel. This one is called Making It Happen, Critical Technologies Investments. Our moderator today is Doug Terrier. Thank you so much for being here, considering. Chief Technologist at NASA. In this role, he is the agency's principal advisor and advocate on NASA technology policy and programs, helping plot the strategic direction of the agency's space technology program. He's worked at NASA's Johnson Space Center, Houston, as the center's chief technologist, as deputy director of NASA's Johnson's Strategic Opportunity and Partnership Development Office, and associate director of engineering, where he led teams responsible for design and development of spacecraft for NASA's Human Space Exploration Program. He also holds patents for his work in aerospace propulsion and has published numerous technical papers. Doug, thank you very much.
Well, good afternoon, everyone. Thank you for being here. Again, my name is Douglas Terrier. I'm the NASA Chief Technologist. I'm really excited to be a part of this first Glenn Symposium. We've got a great, I think, a treat for you today. We're going to talk about my favorite subject, technology, and how that enables exploration. So, if you think about it, we're really celebrating NASA's the 50th anniversary across the nation. So, this is a great time to be here. In fact, celebrating NASA's 60 years of, beyond 60 years of exploration and discovery. If you think about the first 60 years, what we've done, everything ranging from John Glenn's first historic orbital flights in '62 to Neil Armstrong on the moon. We've flown 135 shuttle flights. We've built the International Space Station. We've really created a commercial infrastructure in suborbitals, in Earth orbit. And beyond that, when you look at our science mission directorates, we've visited every single planet in our solar system with robotic vehicles, and we've had some Voyager go beyond the solar system. Really amazing achievement. On the aero side, equally amazing. We've helped to create a probably $10 trillion global aviation enterprise and secure America's leadership in that. No small feat, and we continue to do that. The great observatories like Hubble have unlocked secrets of the universe, rewritten the textbooks, and we have more to come. So all of these feats are really driven by the technology that enable them, and so we want to talk about that. The other part of that's really important to stress is that for every dollar we're putting in here, we're probably getting somewhere, depending on who estimates, it's probably 7 to 10 times return in the national economy and economic value, quality of life across multiple industries. If you look at what we have going forward, right? So starting with the Artemis program, which will return humans to the moon and the first woman on the moon, we have commercial space enterprises really just blossoming all around us. On the science side, we've got a new generation with James Webb and a new generation of both telescopes and robotic explorers looking for signs of life and some really exciting opportunities there. And of course, Aero, for the first time, I think, in a decade, has 3 named X-planes out there flying. It's just really an exciting time for all of us. And again, there are a lot of challenges in front of us, just as there were in the previous decades. And we're going to be developing the technologies to overcome those challenges. So, and of course, that will also have this similar return, which we can't often predict. But I think it's really important. We always remind people about the return we get across the economy, both in economic value and in inspiration for younger folks, and frankly, in American leadership globally. So nothing could be more important than the mission we're doing. What I'd like to do for the next few minutes, I'll start by introducing our panel. We've got an excellent star panel here, and then I'm going to ask each of the panel members just to briefly introduce the challenges in their particular area and some of the technology investments that we really need to focus on. So I'll start by introducing Bob Pierce, representing the Aeronautics Mission Director. Next to Bob is Ken Bowersox, representing HEO, and Dr. Joel Kearns is here representing SMD, and of course Jim Reuter representing STMD. So we've got a very stellar panel here. And let me kick it off by just asking you, Bob, to talk a little bit about what are some of the big things going on in Aero, and what are the challenges, technology challenges in that?
Sure, thanks, Douglas. And when I was looking earlier, at the dates there, and I was thinking about the history of NASA. And of course, aeronautics, we go much further back than even NASA, right? So we started with NAC and so forth. But I was thinking about those dates, and it's really interesting. So 1958, obviously, NASA, 62. The first flight for John Glenn, and then in '69 we landed on, so in a very short period of time, right? Tremendous development and progress and accomplishment. And so I was thinking about from an aviation perspective, so So 1958 in aviation was the first commercial flight of the Boeing 707. And between 1958 and 1970, so a very similar time period, was the 707, the 727, the 737, the 747, the DC-8, the DC-9, the DC-10, and the MD, and I'm sorry, the L-1011. All of those vehicles in that period of time were developed, first flight, and entered into commercial service. So the dawn of modern aviation was in that same time period as sort of the dawn of human space travel. So it's a really interesting synergy. And as we look, and so what were the ingredients for aviation? And we had a panel this morning on supersonic, right? So two big ingredients, right? You need the technology and you need a market. Either one of those things are missing, nothing's gonna happen. So as I look at where we are today in aviation, and again, it's sort of an interesting parallel as we look at maybe another great generation of human exploration. I look at aviation, and we are on the verge, I think, of another great set of innovations as we go forward. And it's really, and part of it is driven by that technology, a lot of which NASA has pioneered and laying out that technology pathway. But it's also driven by a set of challenges and a set of opportunities. So on the challenge side, I don't know how many people are aware of it, but in Europe right now, there's a big movement around what's called flight shaming, right? Because of carbon footprint and so forth. And it's a social media driven issue that's popping up, and it's going to find its way into regulation eventually. So, Europe is going to really tighten things up on the environmental side, especially on the carbon side and efficiency side. We're going to have to. This is a global industry. We're going to have to meet that challenge. There's ways of doing that. On the purely competitive side, you've got most of the market is going in the Asia Pacific region. China obviously wants to be a part of that market. They want to be building these aircraft, these systems, and selling those systems. So we're going to see a lot of squeeze in terms of the need for performance, especially environmental performance, and the need to compete against a burgeoning set of sorry, I know I'm supposed to. Yeah. So a burgeoning set of competitors, and at the same time, there's an opportunity, and let me see if I can do this. So in that market,
Can we advance the charts, please?
yeah.
I don't think the clicker is working.
I'll just say the two areas I was going to emphasize. There we go. So you saw the vehicle on the top, right? That's the X-59, and on the bottom it's the X-57. So those are two of the X-planes. We're not quite flying the X-59 yet, but soon enough. So two areas that I think are really critical when we look at both opportunity as well as those constraints we're going to see relative to environment and to competitiveness and so forth. So on the top, the reopening of that supersonic market, that civil, the commercial supersonic market, as you look at the need to further integrate, further shrink the globe as those interconnections across the globe become more important, as that travel continues to grow. We need to go faster in order to make that a more efficient traveler experience, both especially for business, but also for the cultural integration that we can achieve through that. So we're on the verge in just a couple years, as you heard earlier, of flying that particular airplane. And that airplane is built for a very specific purpose, which is to set a standard for overland supersonic flight. If you're probably aware today, commercially, there's a prohibition against overland supersonic flight, and it's because of the sonic boom. So if we're going to do this, we need to soften the boom. That vehicle is specifically developed to generate a boom level we believe will be acceptable, but the regulators need us to go out and fly that over communities, get that community response, deliver that data to them so that they can make the rules necessary. There's a whole bunch, and so we're doing that. We're on track to make that happen, and the regulators are with us, and so I think that's going well. There's a whole set of issues, landing takeoff noise, other emissions and so forth that have to be done. We're knocking them off one at a time, but the nice thing is, so we're doing that. We're doing the technical work, we're doing the research work, but there's innovators out there. There's commercial innovators out there. I believe there's a market out there, and again, you heard that earlier. Down below is the X-57. That's distributed electric propulsion aircraft. So electric propulsion as part of that environmental solution set is becoming more and more recognized amongst industry and amongst the aviation community as a key solution set. Now, this is relatively small scale, but we're looking at megawatt plus scale electric power. So these are, not large in size, but large in power, motors and power electronics and so forth that have to be incredibly efficient. You got to manage the thermal, you got to manage arcing, EMI, all those kind of things. There's a lot of technical work to be done there. NASA has been innovating in that area and leading that area, and now industry is quickly following behind us, and in the next few years, you're going to see us quickly moving into not just flight with this vehicle, which is a couple of hundred kilowatts, and will be enabling for smaller applications, but we're going to be getting into flight with megawatt scale electric power and proving that out so that the industry has that available for the next generation of products. The other market that's really, really interesting, am I going the wrong way? Maybe. Oh, it's this way. Ah. You got to push the door the right way to get out. The other market that's just really fascinating, really is burgeoning right now. Of course, UAS, whether that's large UAS wanting to fly in regular airspace, or small UAS, which is the really sort of really exciting one. Small UAS flying at low altitude. NASA and the community just finished in the Reno area a set of flights where we flew 150 missions downtown Reno using UAS, using a UAS traffic management system. Planned off nominals and real off nominals occurred, and the system worked exactly as it was supposed to. And there was 150 actual missions and 500 simulated missions worked, and now we're going to Corpus Christi doing the same thing. First ever, and it was NASA and the community working that together. And where they want to go is urban air mobility, which is essentially electric VTOLs at an air taxi size, so 3, 4, 5 passengers. So relatively large vehicles, all electric. Doing urban transportation. It's an area that we're going to. This was challenging. This is going to be really challenging, right? Because you have noise issues, you have airspace integration issues, you have major safety issues. That was discussed earlier. There is no going back and thinking about this as a Wild West. Right out of the chocks, this system is going to have to meet commercial aviation safety standards. Otherwise, it's never going to go anywhere. That's an incredibly tall bar. In the U.S., there's been one fatality in commercial aviation in the last decade. One person. I mean, it's an incredibly high bar, but there's no going back to the way it used to be and say, hey, well, we can live with a high accident rate for the next few years as we work out the technologies. Can't happen. So what NASA's going to do is develop a proving ground, let industry come in, work with us, and actually prove out that these systems are safe. So just a taste of some of the things, but we are really on the verge of. Since that period of 1958 to 1970, I think we're on the verge of another period of about a dozen to 15 years where you're going to see innovation at the same scale. Thanks.
Great, thank you, Bob. Ken, let's ask you to give us a HEO perspective.
All right, could we get to the next slide?
Down arrow.
The down arrow.
Maybe. That's down.
Okay, well, I want to talk about some of the challenges that we have in human exploration and operations that we'll address with technology development. And I wanted to start here with the policy that kind of guides what we're doing and pushes us towards developing that technology. The desire to lead an innovative and sustainable program of exploration with commercial and international partners, and to enable human expansion across the solar system to bring back to Earth new knowledge and opportunities. I really love this policy directive because it's not just about what we do in low Earth orbit. It's not about going to the moon. It's not about going to Mars. It talks about the high-level goal of moving humans away from Earth and out into our solar system. And I get a little emotional about this, but someday we're going to go outside of the solar system. It's way off in the future, but it's going to happen. Whether it's 1,000 years or whether it's 2,000 years, it's going to happen. And that I really love about this particular directive. Here's another picture I like. I like it for a lot of reasons. It's pretty famous. It was taken by the Curiosity rover on Mars looking back at Earth, and that little dot is Earth. It helps to remind me about our challenge, our technological challenge of moving humans a really long way through an airless void from one planet to another. It's a really, really large challenge. And to balance the technological requirements with the risk level we're willing to accept, along with the cost of that technology and the size of our economy and the amount of money we can afford, it is going to be difficult. Well, this also reminds me that we've crossed that barrier and achieved that balance in robotic space exploration. I don't think we're far away from achieving that balance in human exploration. Again, whether it's like a lot of us hope in the next 15, 20 years, or whether it's 30, 40, 50 years, we're very, very close. So what we're doing in human exploration and operations is kind of a coordinated attack in all those areas. We're trying to develop technologies and capabilities, lower risk, lower costs everywhere we can across the spectrum to move us from the surface of the Earth out into the solar system. It starts in low Earth orbit with the International Space Station and other spacecraft, some of the commercial work we're doing there. It's going to move to cislunar space with the Gateway solar electric propulsion work that we're going to do to help us lower the cost, the amount of mass that it takes us to get to Mars. The work that we're going to do with landers, reusable landers on the lunar surface, looking for resources. And someday, we hope, even newer and better types of propulsion that will allow us to make the trip faster as those propulsion types become available and become economical. So I think there's a lot of work to be done in this area, and I'm excited to watch it develop over the next 10 or 15 years.
Thanks again. So we'll ask Joel to speak from the Science Mission Director's perspective.
So there are three distinct themes for the scientific research that NASA enables and sponsors. All of them are really seeking to generate new scientific knowledge for the benefit of the United States, world, our international partners. But they all rely on engineering development, which in turn all relies on technology development to enable looking out further into the universe or looking in more detail at the solar system or our own planet Earth. So the three themes that are focused on and drive the technology development and Science Mission Directorate. First is looking for the life elsewhere, and you can see on the image here, we highlight the rover on Mars, Curiosity rover, but it's broader than that. It's looking at other places in the solar system, following the water to places like Europa around Jupiter, Enceladus, or Titan around Saturn, maybe Triton, around Neptune, and all the work done, for example, in some of the observational missions like Kepler, looking for Earth-sized planets in habitable zones around other stars, and all the broad work that's done in astrobiology to even look at physics and chemistry in space and how we can predict whether the conditions exist for life in other places. And then, of course, there's a focus on protecting and understanding our home planet, whether that's global climate or agriculture, disease vectors, the radiation budget of the planet, the energy budget. And then something that we think of traditionally for science, which is observing out there, sending probes to other planets just to investigate those other planets, having the great observatories that started with Hubble, and then the later observatories leading up soon to the James Webb Space Telescope, which will launch relatively soon. But as we look further and further, we find as we answer questions, we have more questions that require more detailed instruments, mission technology that still have to be developed. So SMD sets directions based on both advice that's given at a national level from the National Research Council, National Academy of Sciences, through surveys every 10 years in these different thematic areas like astrophysics or planetary science or heliophysics or earth science, but also from competitive calls for investigator-initiated research. And that's how the science goals are set, and that's also how the technology development goals are set. SMD in general develops its technology through issuing broad calls for investigator-proposed research based on peer review. The top efforts that meet the NASA overall science goals are selected, and they progress through technology development up to various technology readiness levels. And you can see here, I'm sorry, I went a little too fast, that you get there in some metrics on the types and the amount of research that are sponsored by SMD. not only for scientific research, but technology development, what type of investigations are done, for example, in aircraft and balloons, and the large number of space missions that are either in development today or operating today. There's an unprecedented number of operational science space missions going on right now, compared to if you look at a NASA science portfolio from 20 or 30 years ago. And also trying new approaches like very small satellites or CubeSats to try to get rigorous scientific data using those small platforms. As you can imagine, it takes quite a bit of technology investment to be able to pull out rigorous measurements you can trust from very, very small space assets. So one of the flagship missions, of course, you'll know is coming up is the James Webb Space Telescope, which is a large infrared telescope, a near-infrared, which is the successor to the Hubble Space Telescope. Some of the technologies that had to be developed for that might surprise you. For example, Ka-band software-defined radios that were developed by NASA, for example, at Glenn Research Center, allow greater access to the EMI spectrum, and they enable some of the work that will be done and how the James Webb will operate. They allow for faster transmission of scientific data back to Earth to support the various mission objectives and investigations that will go on for a Webb. And today there's over 250 orbiting software-defined radios hosted on payloads, as will be done for the Webb Space Telescope. And in the software-defined radio, the initial work on that was done on the Space Communication and Navigation's testbed up at the International Space Station was recognized recently with a Space Technology Development Award out at the at the Space Symposium in Colorado. One of the newest missions that was just announced that's been selected for full-scale development is the Dragonfly rotorcraft spacecraft that will be sent out to explore Titan by air. You heard earlier that there is a helicopter on the upcoming Mars 2020 mission. That's a aerial vehicle that's optimized for the Martian atmosphere. Titan's atmosphere is quite a bit thicker, different temperature, different chemical composition. So the mission has been developed as part of the New Frontiers program and recently approved for full-scale development to actually send a flying vehicle out to Titan that will then follow on from the Huygens probe work that was originally done with Cassini. However, to have this system operate, you not only need the rotorcraft, but you need a reliable power supply. And this particular system will use radioisotope power generation systems that have been used successfully for a number of science missions over the years. They were used, such systems were used to support human exploration in the Apollo missions. They were used most recently on Curiosity, and this will be the next mission that will use radioisotope power systems. Locally, we know that Glenn Research Center specializes in space environments, simulation, and testing capability. One of the things that is used for Science Mission Directorate here in Cleveland is called the Glenn Extreme Environmental Rig, which the way it's currently configured can simulate the high pressure, high temperature, and chemistry of Venus. So people that are now responding to decadal survey themes in the long term to look at probes to go up and explore the surface of Venus, whether that's landers or maybe flying vehicles, now have an ability to develop components and mature technologies for probes that could actually operate for extended periods on the surface of Venus. What you would look at, if you looked at the Venera probes that the Soviet Union sent in the 60s and 70s, extended time back then was probably on the order of minutes. And SMD is hoping to use this new test facility to have researchers around states develop technologies that will last for much longer times than that, so that meaningful long-term measurements of the environment and scientific studies on Venus will be possible. So, of course, almost all the work I talked about here is robotic, remotely controlled spacecraft that are used either in space or looking down from space on Earth. There's also piloted work that's done, for example, in airborne measurements where aircraft are used to fly and prove out astrophysics technology or earth science technology, first on aircraft such as the Sophia aircraft or the DC-8 based out at Armstrong Flight Research Center. Those can either be standalone investigations for scientific purposes, or they can be used to mature technology, which is later used for spaceborne missions. Now I'll pass it over to Jim.
Yeah, so underpinning all that we've just heard is, of course, Space Technology Mission Director developing the cross-cutting fundamental work to support all these missions. So I'll ask Jim to give us some brief on that.
Okay, thank you, Douglas, and I want to thank everyone for inviting me here. It's a real pleasure. I always enjoy coming to Cleveland. That's not even a part of a joke or anything. But it's especially rewarding to be coming to your first annual symposium for John Glenn Memorial. I can tell you that is not an easy thing to have pulled off, and you deserve a lot of credit because it's obviously a huge success, is what I see. And so I really applaud you. Thank you, and thank you for having us here. And what we like to say in space technology is that it's technology that drives exploration. In terms of putting together our strategy, we think in terms of how we do our investments, we think in terms of what we call four strategic thrusts. And then we kind of have a one-word name for each one of them is go, land, live, and explore. And so for go, it's look for rapid, safe, efficient space transportation. One of the fundamental technologies that we can have that be truly transformative how we go about space is extremely rapid transportation. And so part of our investment strategy is to do those things that are not just the evolutionary things, but the revolutionary items. And in this case, they almost all involve nuclear fission in one way or another, whether it's a power generation or propulsion implementation, but that's there. And on top of that, then we're looking at things that are more evolutionary. And we do that, a large part of our investment strategy is looking at the exploration campaign. And what we try to depict on this picture is that aspect of it, is that our target, we start from where we are today. Our target is to achieve ultimately a human Mars missions. As one of the fundamental targets we have. The best way to go through that is really through the Artemis program that we have and through the moon. And so what we try to look at is what are those technologies that we can do that the moon is our proving ground. And that's what we try to depict here is some of those technologies, as well as then what are those other unique technologies that we have to develop to get to Mars, but really there's no application for doing it on the moon. But as we try to show on here is a large part of what we do actually can be demonstrated in the near-term environment of 3 days away on the moon, and then have that apply towards Mars. And so in that regard, the gateway, one of the first elements, the power and propulsion element, I think tomorrow we'll hear a talk on that. And we're providing 4 technologies that would get to boots on the ground by 2024. We also try to support a sustainable presence by 2028, and then beyond that to Mars. Our definition of what a sustainable presence on the moon is still evolving, but fundamentally the number one criteria for that is, have we accomplished enough on the moon to enable Mars? And so from the standpoint of the very first element of the gateway, enabling 2024, we're implementing a very high power solar electric propulsion system that's being developed right here at Glenn and with their contractors through Aerojet Rocketdyne are all here. And so that would enable a 50 kilowatt basically system, for electric propulsion. We are also looking at, especially as you evolve to larger scale human landers, efficiency will drive you towards cryogenics as part of your propulsion system. And a lot of those, especially since it appears that the propellant of the universe is water, a lot of that is really in the form of stored liquid oxygen and liquid hydrogen, which also can be a source of power for short-term stays. And so, And so a key part of what we're doing here is looking at that, enabling long-term storage, which enables a lot of the human exploration on the moon, but also then feeds forward to transportation systems throughout the solar system. We also, as another thrust, we're looking at, is the second thrust that we'll talk about is land. Basically expand our access to diverse surface destinations. And for us, that starts with precision landing. We see large aspects of that here, incredible aspects on what SpaceX and Blue Origin do here. But also there's technologies we're developing that are working with the providers for lander services to enable precise landing on the moon that will also carry forward to Mars. But Mars has an atmosphere that's kind of an anti-Goldilocks atmosphere in that it's too thick to be easy to get through. Too thick to just land, but it's too thin to help slow you down. And so hypersonic deceleration is something that can be implemented a few different ways, but we have one of our implementations that we're doing right now is a demonstration on an Earth environment with a public-private partnership with ULA that looks at a 6-meter, basically inflatable hypersonic deceleration that would have to grow to about 18 meters or so to go to Mars. Then the third area is live, providing a sustainable living and working farther from Earth, and then as well as explore to enable transformative missions and discoveries. And what we look at is the moon to be kind of a platform for a lot of technology demonstrations. What we're implementing is what we're calling a Lunar Surface Innovation Initiative, which is really a public-private partnership platform for us to investigate technologies of what you would do once you get to the surface. So it's things like dust mitigation, in situ resource utilization, surface excavation and construction, extreme access and extreme environments. Those are sort of things that we're looking at that have a broad interest and enabling capabilities. So in order to implement some of these things, we try to use our entire portfolio what we're trying to say is the best way to innovate is through competition. Exploration requirements drive technology, and our technology drives what we can do in exploration. So what we're trying to do is look at every platform available or acquisition strategy approach that we available to create competition as we're going through this. Having the multi services of commercial landers that's being implemented by Science Mission Directorate, having a competition model for human landers and services enables a platform that we can really engage the community. So it's a broad range of things, and just as a few examples of the things we're trying to do is we have this NASA Innovative Advanced Concepts or NIAC program. That's been something that largely has been studies to this point. The only real criteria to get in is that you have a revolutionary concept that doesn't violate laws of physics. What we've done this year is implemented a phase 3 to that thing, and with that we've just recently awarded a couple of awards. One of which is actually we intend to implement on the moon platform, and it's a way to rapidly survey craters and look for underneath structures and stuff like that. Also, from that, this is a great opportunity we vision for crowdsourcing. One thing that I think we're looking real strongly at is how do we implement crowdsourcing in some of the acquisitions or ideas that we may come up with. We think lunar dust mitigation is a really good area for that. Excavation may be another. We also are looking at prizes and challenges and implementing those on something that, say, would give us a rechargeable way to get through a lunar night, a battery or energy storage device that would get us through the night that's rechargeable. Lunar night is about 350 hours. And so that's the kind of challenges we're looking at. We're also looking at forming a consortium with universities and other partners and stuff where all of us will have some skin in the game of the types of things we do. And we think with the capabilities that are being enabled on the moon, we can kind of enable those. And so for us, it's an exciting time. It's the technologies that we're driving that will drive us towards exploration, transformative around the whole solar system. Thank you.
Thank you, Jim. Hey, so you mentioned quite a few different kind of mechanisms there for engaging with the sort of innovation community around us. So you mentioned public-private partnerships, prizes, crowdsourcing. Can you just briefly say where you think those fit? You know, what's the right application for each of those kind of tools to engage other folks?
Yeah, let's see. Part of what we try to do is help enable the services development for human landers, for commercial landers and platforms like that. For those, it works well for us to have some form of public-private partnership solicitations. We might use the Next Step BAA process for those. We have a tipping point and an announcement of collaborative opportunities, and those are ones where basically then NASA expertise is brought in, NASA facilities are brought in that works with the ultimate supplier, and it's a proposal, but it's then a close working relationship. We think the Moon, as I talked about some, is a great platform for looking at things like crowdsourcing, engaging community and engaging multiple ways to get for technology developments. And the CLIPS lander is an opportunity for us to be creative. We don't have to worry about things, not about whether there's a failure or not, because what we want to do is learn and try, and then and involve competition as we go along. So there, NIAC ends up being a really good place. We have an early career initiative inside NASA where it's at a place where we encourage young people to actually lead the projects that we go through it, and so it's a platform like that. Crowdsourcing I talked about is on the surface, and so it's really all those as we go through it.
Thank you. I'm going to ask an aero question since I have an aero guy beside me.
Okay.
So I keep reading a lot about hypersonics and suborbital flight, even in some cases. Of course, we're focused on overland supersonic flight as the next. Do you foresee a future where those things materialize in commercial aviation?
Hypersonics?
Yeah.
Yeah, so right now, the big push, of course, in hypersonics is on the military side. So what we're doing is relatively foundational and fundamental work, basic physics, some work around mode transition for dual mode type engines that would go from a turbine to a scram and so forth, so how you make those transitions, do that automatically and so forth. We're doing work like an uncertainty quantification. Think about hypersonics, right? Lots of thrust, lots of drag, just little errors could ruin your day, right, in terms of the ability to accelerate and actually achieve hypersonic speed. So where your uncertainties are in your design, so you can put effort there is really important. So we're doing a lot of that foundational stuff. We're using DoD because they're going to flight, they can generate data, we can instrument generate data, and then we can validate the kind of work we do using flight data, which is hard to come by. Now, beyond that, we are starting to see interest by the commercial sector in hypersonics. Some are thinking, well, we're just going to bypass supersonics altogether, go right to hypersonic. But there's other, so point to point, across the globe, other forms of, sort of filling logistical holes and supply chains and so forth that you could do through hypersonics. Those ideas are in their infancy. It's getting the margins you need to actually close on an actual transportation mission is tough, but the interest is there. So what we would like to see is, as we develop the technologies and validate them together with DoD, we start to look then how can those apply in a commercial way, towards a civil mission. And honestly, there's a whole history. That's kind of a synopsis of the history of aviation in some ways, right? Do the fundamental research. DoD takes a lot of risk, puts those into flight, and then we see how those applied to civil. Now, it's become a lot more complicated since then, but I think in hypersonics that kind of model still holds. So they're out there, but we're probably a couple decades off.
Yeah. Okay, great. Thanks. I'll ask one more question. I want to leave a little time for audiences, so you guys think of questions if you've got anything. This is a great panel to pose to. Ken, I want to ask you a question. So, as a 5-time spaceflight veteran, what do you think the differences and the challenges are when you think about station versus gateway versus long duration flight out to Mars, for example, from the perspective of the crew and the countermeasures and so on?
Well, if you look at what we're doing on space station, the studies we're doing with the crew are really focused at a long duration transit to Mars. The 6-month mission increments, the type of analysis we do on the crew before and after flight. That's to build up an experience base for what we think is a typical length of the mission to Mars. But that's one way, right? And then you land on the surface, you spend some time on the surface, hopefully recuperating, and then you do another one of those 6-month missions or more back. Even what we're doing on space station now is less than the challenge we'll have when we go to Mars. At Gateway, the challenges we have, I think, are going to be more with the equipment than with the humans, but it's important to develop that equipment. And the missions will probably be a lot more like shuttle missions were, I think, or like Apollo missions. And then especially on the lunar surface, those will be like they'll be like Apollo missions, but then we'll spend more and more time on the lunar surface and do more and more things that we didn't get a chance to do when we were there with Apollo. That's kind of the way I see the continuum, but I think we're building up the necessary experience base that we need to accomplish all those missions.
Thanks. So I think we've got about 10 minutes or so. Any questions from the audience?
Yeah, thanks, Doug. So we'll start again with the questions that have been submitted and upvoted through the Conference IO interface. So the first question, so how do your organizations determine when it's time to divest a technology area that might not be important or necessary for the agency's new near-term goals, such as going forward to the moon by 2024?
You want to take that, Jim?
Did I say that I really like being in Cleveland? No, that's a really tough question, especially for a government agency. Divesting is something that's not necessarily the first thing in our culture. So it is a hard thing. But what we do is when we manage programs and projects, we go through key decision points as we go through that, and with that we get all the right folks together, and it's a formal time for us to go through and decide, have we gotten far enough on is the development on schedule? Is it still viable? Is there still a need for us? And so there's, for those major projects that will go through that, then we kind of go through that assessment. What we try to do is, as a mission directorate, is once a year we go through an annual assessment, and so we go through an annual review of each of our projects, and with that, then that's a big part of that goes through and says, well, what's your infusion strategy? If we don't have an infusion point for our technologies, then why are we doing it? There can be reasons we do, but that's part of at least the discussion. So we try to do that, try to keep close with our stakeholders, and then also through the major projects go through key decision points.
And if I could add, I think having worked with you closely on some of this, I noticed if maybe not the question posed is sort of binary, it might be about emphasis or priorities, right? Would you say in some cases?
Yeah, absolutely. And that's a lot of what we do is balancing our priorities. There's a lot more technologies that we'd like to develop and invest in than we have capability to do so. And that priorities do change as our stakeholders' priorities change as well.
Great. And again, if there's a question in the room, please raise your hand and wave it a little bit and so we can see, and we'll get a microphone over to you. The next question, what do you see as the most difficult barrier in advancing technologies before other countries?
The U.S. ahead of other countries? Is that
Correct.
Yeah, so, I think that the United States has obviously been a leader for decades, and we intend to continue to be a leader. I do a lot of work with the other parts of the government that focus on these questions. And one of the things I think would be, it's pretty hard not to ignore, is the fact that certain countries have very long-range plans, strategic plans that they are executing very methodically. And though they may be behind us right now, and you mentioned this when you talk about the pressure on some of the airplane market, for example, Bob, their investments have been very consistent, and they're making really good progress. I think we naturally, getting back to back to Jim's point about we balance priorities, and our nation balances priorities at least every 4 years, and that's, I think, the biggest hurdle for us to push some of these things forward consistently. My opinion. Anybody else?
Yeah, I think I would just add that I think, we as a nation, I think have become more risk averse, right? And especially in technology and technology application. Like I said, if we're going to introduce a new aviation system, it's going to have to be as safe as commercial aviation from the get-go, right? Or things are going to slow down or stop or reverse. So other countries may not have that same kind of risk aversion. So it does, in some ways it gives it. So that's one. The other one is, of course, the ability to leapfrog. If they don't, we have lots of infrastructure, and that infrastructure costs a lot to upkeep and so forth. And If you don't have that infrastructure, you can go to the next technology. So that's certainly an advantage as well. I think we need to take those challenges and just address them head on, and not be afraid to take take these challenges on. If we sort of say, look, there's no way we can compete because they have these advantages, then we sort of give up. I think we can do it. I think we've got the kinds of expertise, technology, and will to make those things happen. But you have to take it on head on.
And I'll just add one contrarian item, and that is part of our history is we're used to being the best, so we sort of assume we still are. And so part of our hurdle can be to really convince ourselves that maybe somebody else is catching up or passing.
And something else, I mean, we've been charged in SPD1 to work cooperatively with other countries. And sometimes that means instead of trying to be the first to develop something, we have them develop it so we don't have to pay for it. And there's a balance that you have to find.
So then this other question that's on here kind of goes directly to that. The question verbatim is, SPD says to achieve goals with commercial and international partners, we apply the Buy American principle. This prevents us from taking advantage of international innovation. So what's more important, success, speed, innovation, or protecting the U.S. industry? Do these goals and restrictions operate across all of NASA?
What I see is we have to find a balance there. We try to develop U.S. industry, but at the same time try to work with international partners, and there are competing goals. And whenever you have competing goals, you have to work really hard to see if your balance is right. And it's a challenge. And I can give you 10 of them that we work every day.
And yeah, I'll add too is as you go through that assessment of where is it that you would want to retain it in-house in this country versus going out to somewhere else, it becomes a question of which are these technologies one of national interest. And those that are the ones that we have a primary national interest are the ones that we try to would prioritize in-house. Those that we think we can accept and can be ones that you'd work with internationals.
I'd add, from a scientific research point of view, that it's important to use international partnerships and their resources to enable opportunities for American scientists to make measurements that they wouldn't be able to otherwise. And at the same time, it's important to recognize that part of making a measurement or making an observation is developing the equipment and the technology that allow that measurement to be possible. So there is a bit of discussion deciding whether something will be done in the United States or will take advantage of international partnerships about whether we think the technology development associated with making the instrumentation to enable those measurements is something that would be beneficial to have done in the United States, or it's fine to take care of an international capability. Of course, there's some capabilities in measurement that are better done by international bodies because they either have more experience or a higher level of technology in some niche area, but that's always a trade that has to be made.
So another one that's at the top of the voting, different approach. Who is leading plans for lunar surface habitats? Seems like ESA is more focused on this effort.
Well, we have work going on inside the Human Exploration and Operations Directorate in that area. I mean, there's an activity that I know of that's going to help us. I'm not ready to disclose any of the details, but we're thinking about it. One of the trades is, do you want a stationary habitat or do you want a roving habitat? What's going to make the most sense from a payload integration and from a cost point of view? And we're making a lot of those trades. And again, we're concentrating on getting there by 2024 initially. And so some of the procurements to make that happen are they're on the front burner, whereas the habitation type studies are a little bit farther out.
Okay. And I'm going to go with this one, even though it's not the top one, because I just think it's a really good question. What are the critical technologies for going forward to the moon that are not currently part of NASA's portfolio? What keeps you up at night?
Let's see. We're trying to address a lot of different ways. In terms of things that are in our portfolio and keeping us up, we really need to have a long-term reliable life support system that's being demonstrated as we're going. ISS is a great platform for it, but it's one that's a high worry overall for the agency. Radiation protection is one that there really aren't great solutions to that. That involves something that we can do. You know, it's one that probably frustrates me more than any others as we try to look at our investment, because it's one of the biggest problems that we could try to address, other than you know, safety standards on the crew members. But it's also one of those that's really hard to find what kind of technology investment can we make that would really make a difference, more than, you know, implementing. So then beyond that, you know, I think a lot of the activities is certainly for the establishing the lunar base. We have technologies that are in place that we're going to be able to do that for 2024. When we look beyond that and say, how do we explore the solar system and get to Mars? Well, then becomes a lot more that become front burners. Like the entry, descent, and landing becomes much more challenging in that environment. How do we get there? The advanced propulsion systems. What kind of power system do we have that's sustainable on the surface? So those are ones that may, the one that bothers me the most is because I'm having trouble seeing what I can do about it is radiation.
Yeah, and for me, you know, the long trip to Mars, it's the human health risks that I worry the most about. For getting to the lunar surface, I'm worried about getting the program and the hardware in place to land on the surface. I mean, I think that's our biggest technological challenge in EO.
I could just add to that. I think, yeah, I agree with all that, and both of you mentioned the long transit time, right? So a lot of radiation risk, the human health risk, the long duration of support, shortening the time is, if there's a magic bullet. So we're looking at a bunch of things and nuclear propulsion, stuff like that.
Propulsion is,
But that's something that's not in hand currently, I would say.
yeah, oh, not close.
And we'll be talking about exactly just that in two of the sessions this afternoon, propulsion and power. So.
And that's why you see the architecture we've got now. You know, it's laid out with what we think we can accomplish in the next 10 years. But if we see a more rapid pace of change in propulsion, that could change things.
Great. We have a question right over here.
How do we maintain the Artemis program beyond just making sure we do a one-time flight, boots on the ground by 2024? So we build on that for the sustainability and global access to the lunar surface. Thanks.
Well, first of all, I mean, that's our intention going in, is that this is going to be a sustained program, right? And I think that an important part of making it sustainable is to do it in a little bit different way than the way we did Apollo. And so, to me, Gateway is really important for that. If you look at Gateway, we're not talking about just stopping at this little spot to visit on the way to the lunar surface. I mean, we're talking about actually using it as a place to aggregate and reduce the risk to our landing vehicles, potentially as not necessarily a full refueling stop, but maybe just a place to top them off. Let's say we use a little bit of maneuvering fuel getting to the Gateway. Well, if we could add just a little bit of fuel when we get to the Gateway to top everything off and get it to the surface, that could lower the amount of mass that we need to lift with a commercial launch with that element. But then we're also talking about setting up this commercial infrastructure around the Gateway, where we actually have commercial providers bringing up different types of supplies, whether it's fuel, oxygen, water, clothing, whatever it is that they bring up, suits. We're talking about doing that with commercial acquisitions to actually start that process, so that if there's ever commercial operators that want to get to the lunar surface, that infrastructure will be in place. And I think it's that type of a more complicated and intricate approach that will make the whole project more sustainable.
And I'll add to that, one key thing is deliver on our commitments. Fly Artemis 1 when we say we're going to do it. Fly Artemis 2 when we say we're going to do it. The CLPS landers and flying them once, twice a year, and getting those going in 2020 and 2021, those go a long ways towards having a sustainable program.
Excellent. All right, so another popular question on here. How do we address the goal of maintaining or reestablishing U.S. leadership in technology amidst the directive to make public the details of NASA's technological advancements?
Well,
Do you want me to say
what
it
I would
again?
say is, you know, like everything, there's competing requirements. We are an open agency. We make public our technologies as we go forward. However, we are still governed by our ITAR rules and other constraints. And so that is a balance that we do of how much do you, when you make public a technology, there's some aspect of that ends up being, in many cases, how much of it do you actually make public and how much of it do you protect under the constraints.
And I'd also add that, you know, there's a lot of benefit that comes from the partnerships we have with, in the case of aeronautics, especially in terms of industry and so forth. There's, you know, there's a lot of knowledge, a lot of implicit knowledge that's built up through the research partnership and so forth, how you do things, and so forth, that isn't captured in you know, just publishing a paper and so forth. We also, so that's one of the other, you know, we need to be able to protect IP, right? So if someone comes to us with an idea that's got some IP behind, you know, we need to protect that, right? So, and there's ways of, I mean, I think as Jim was saying, there's ways of publishing our data that protects IP. So we are getting the fundamental principles out there of a technology without giving away the, you know, the secret sauce that any particular company or organization may have that's behind that.
Okay, last one. Thanks.
With the human being, one of the limiting factors, and particularly for long-term travel to Mars, microgravity has been one of the things that we're continuing to study, as you've experienced, sir. Has there been any initiative or thoughts towards artificial gravity and rotational long-term space stations as we travel to Mars, or even, for instance, spending time on the lunar surface or Mars surface and then going back out and getting your, you know, your G tolerance back up, and all the aspects that go with perhaps reproduction in space, and just how the body develops, the bone loss and those types of aspects of your muscle and body structure?
Well, I know that there's been a lot of discussion of artificial gravity, spinning spacecraft over the years. You know, everything I've seen shows that the cost of doing it would be a lot higher. And because of that, it makes more sense to see if we can just tolerate the environment. And so far, what we're seeing is for the types of trips that we'd need to make to Mars, for example, then we have a really good chance of tolerating the environment. Now, if we learn something on space station that tells us that's not true, I think we're going to have to shift gears. And if we go past Mars, I think we're probably looking at shifting gears and trying to get an artificial gravity for crews. You know, especially if we're talking 1, 2, 3 year transit times out to some really far part of the solar system. Yeah, you see it in all the movies, you know, and but it's hard to do, and so we haven't done a lot of work at NASA in that area, but I think it's something that I would anticipate seeing in the future. But I mean, that's something that would probably start over in the Tech Directorate.
Yeah, and I think you're right, Ken. We in our NIAC program that I talked about, the advanced concepts, we occasionally do studies like this, but really it's a matter of prioritizing our investment strategies, and so far it's been that the cost of versus the gain hasn't been one that's made it a value investment for us.
The things I'd say, even if you look at the science fiction depictions, right, it's usually a very large radius spacecraft, so you don't have a big gravity gradient. Locally, if you did that in a spacecraft size of Orion, that would be really freaky, right? So necessarily that becomes available, at least that approach, when you're talking much larger systems. And I agree with the comment that, you know, long term, we're probably going to have to develop that kind of capability to go further. Right. Well, I think we're wrapping up, and thank you, panelists. Give panelists a round of applause.
Thank you, Douglas.
Thanks for having us, everyone.